So hi everyone. Today I think it's going to be a nice recitation. We will see some short examples or exercises which are I think really nice. So let's recall where we stopped last time. So the setup was as follows. Suppose you have a field F and some valuation V from F star to some ordered group gamma. Then we have the valuation ring OF, all the elements which have non-negative valuation, and the maximal ideal. This is a local ring, maximal ideal MF, all the elements that their valuation is positive. And there is a corresponding place from F to the residue field, which is just this quotient OF mod MF. So this quotient plus infinity, this is denoted as F bar, the residue field. This map, just every element, every function in F, if it's in OF, take it to its coset, otherwise send it to infinity. And then, so this is the familiar situation. And now suppose we have a subfield E. Then we can restrict the valuation to E star and get another valuation from E star to gamma, and the corresponding place, which is the restriction of phi to E, again from OE to ME, the same way. So we have OE, which is just this, the intersection of these two, and this is the residue field, and we can consider it as a subfield of F bar. So this is the setup, and the lemma that we wanted to show is the following. So if E bar is a subfield of F bar, then this is a field extension. The degree of this extension is the residual index. And the image of these valuations is some subgroup of gamma, V of F star, and V of E star, a subgroup of V F star. And both are abelians as a subgroups of gamma, which is order group, so it's abelian. So this is a normal subgroup, and we can talk about the index. This is just the number of, remember, if you have the index G over S, just the number of cosets of this form. So the index of this subgroup here is called the ramification index, and the lemma says that the product of these two is bounded from above by the degree of the extension F over E. So if this is a degree n, then in particular, each one of them is at most n. So we started last time, so let me recall. So the proof started like this. So
the left part is like as vector fields, the middle part is as groups, and the right part is vector fields.
Good, yes. Yeah, so it's field extension, so it's just the dimension of F as a vector space over E.
So this is F bar over E, and the middle is like S groups. Like
yeah. So yeah, good. So we will see it today when in the end of the proof. So we started like this. So say this index, suppose it's M for some integer. So we can find M elements in OF such that their cosets in F bar are linearly independent over E bar, right? F bar is just this quotient. So if this dimension is M, we can find M elements here represented by x1 to xm in OF, such that their cosets are linearly independent over E. And so, and of course, if this is infinite, then M can be as large as we want. And this one, if it's N, then we can find N elements Y1 to Yn in F star such that their valuations in V F star represent distinct cosets in the quotient group. So like there are n cosets, so the elements of the representative little g, small g, is just v of some element from F star. So this is vy1 to vyn represent distinct cosets in this quotient group. And we said that it's enough to show that if we take the set of all elements x, xi, yj, subset of f, it's enough to show that it's linearly independent over E. So if both are finite, m and n, then we find m times n elements in F which are linearly independent over E. So this is at least m times n. And if one of them is infinite, then m or n can be as large as we want. So this must be infinite as well. So we can find a linearly independent set of arbitrarily large. Yeah. So, okay, so what we did last time, we proved the following claim. Oh, so suppose, so we want to show that this is a linearly independent. So suppose there is some linear combination ai, j, xi, yj, j from 1 to n, I from 1 to m, which is 0. Aij are belong to E, not all 0. And we want to get contradiction. So suppose there is such a non-trivial linear combination, and good. So we showed last time the following claim. For every g, for every j, if we take the coefficient of yj, the valuation of this coefficient is actually the min I vaij. So for this fixed j, consider all the element aij. We can assume without loss of generality that one of them is non-zero. Otherwise, we drop this j in the summation. And then we show that this is equal to the minimum, and this minimum, this aij, which means for the I that minimizes, cannot be 0, right? Because there is some aij which is non-zero, so its valuation is finite. So the minimum, in other words, this is finite. Okay. So in particular,
the x are linearly independent over E bar.
The proof of the claim uses the fact that these x bars are linearly dependent over E bar. This was the proof that we did last time.
Okay.
So we use this when proving this claim. Yeah, but I want to repeat. So all we need is, in particular, this value aij xi, I from 1 to m, belongs to V of, so the aij is some element in E and non-zero since it's finite, so it's in V E star. So this is the thing that we'll need. Okay. So it's just a V of some aij and non-zero. So element belongs to this group. Okay, so to finish, so we, oops. So in this equation, So we have the following situation, and okay, so is it possible that so the first thing, what can we say about n? Is it possible that n is 1? So if n is 1, so this is just ai1 xi. This sum cannot be 0 because its valuation is finite. So this is non-zero. And y1, can it be 0? The yj's are from f star. So the first term in this sum is non-zero because this is non-zero and this is non-zero. In other words,
this dot can be 0. Both yj and this sum can be 0.
Right. So yeah. So we know that. So I claim that n must be at least 2. That's what I'm claiming. So right, if it was 1, then either this should be 0 or this, but this cannot be 0 and this cannot be 0 because the claim said that its valuation is fine. And now we have the following situation. So suppose we have a simple exercise in valuation. If we have valuation of sum of n things where n is at least 2, and the valuation of the sum is 0, then I claim that there are two distinct I and j with the same value. So why is this true? So it's an exercise in valuation. So if this is not the case, then without loss of generality, then we can assume that VB1 is strictly smaller than VB2, then is strictly smaller than VB. So VB1, VB2, right? Without loss of generality, if we cannot find such I and j, this is the case. And then what is the valuation of this sum? VB1 by the strict triangle inequality, and yeah. And VB1, sorry, I stated, yeah, good. So this is the assumption. Okay, now it's, sorry. So if we have the sum of n things and at least 2, which is 0, then 2 of them must have the same valuation. Now it makes sense. Okay, so why is that? Otherwise, without loss of generality, VB1 is less than VB2, less than VBn, and then the value of the sum is the value of VB1, but the value of the sum is the value of 0, it's infinity. And infinity cannot be strictly less than. Okay, good. So let's apply it to this case. So we have, these are our BIs, BJs. And then we can find a KNL such that the value of BK is the value of BL. So yeah, BK is this. Okay. And now let's so what's the contradiction? So let's write it. So what is VBK? It's right. It's the valuation of this AI K XK plus the valuation of where I runs from 1 to M plus the valuation of what? YK, right? And same here, V of so if the sum of them is 0, if there is no, so without loss of generality, VB1 is smaller than VB2, smaller than VB. So by the strict triangle inequality, VB1 should be the value of the sum is just VB1, but the value of the sum is infinity, and VB1 cannot be infinity since it's smaller, strictly smaller than VB2, for example. So, yeah.
So, okay, but otherwise they're all 0.
Yeah. So, in fact, in this case, we get that a right, ILXI plus VYL. But and now what is the contradiction? That and this means that the difference between VYK minus VYL is the difference between V of this, which belongs to VE star, and V of this, which belongs to V star. So V of this minus V of this is also belongs to V star. So VYL and VYK belongs to the same coset in this group. So this is the contradiction. Okay, so this is clear. Good. So this was from last time. And today, okay, so the next thing today is to consider the counterpart. So we started with F and reduced to a subfield. Now let's start with E and take a field extension. So a theorem that which will not prove, we could have done it, but it's at least 1 hour and it's like a lot of technical algebraic technicalities and Zorn's lemma. So I'll just state the theorem. Question?
The ramification index, is it the multiplicative group or the additive? Like taking V F star over V E star?
Right, so
the cosets.
So it's VE star and VF star are just subgroups of the ordered group gamma with say plus operation. This is the operation of the ordered group. So with respect to this operation, like in our case, it will be always a Z because the valuations are discrete in function fields. So Z with addition. So the theorem, so if we have some field F0 and L, which is algebraically closed, and a place phi 0 from F0 to L plus infinity, and we have some field extension F above K, then theorem states that and L is algebraically closed, then you can extend phi 0 to a place 5 like this. So the restriction of phi to F0 is phi 0. Okay, so this is the theorem. So the theorem is just let F0 be a subfield of F and L some algebraically closed, and phi 0 a place. Then every such phi 0 can be extended to phi from F2. And a nice corollary, if F over K, let F over K be field extension, and X over F transcendental over K, then there exists valuations V and V prime on F, which are trivial on K such that v of x is positive and v prime x is negative. So in case of function field, f over k, if it's a function field, then every element in f which is not in K is transcendental. So every function which is not in K, not constant, has a 0, the place corresponds to V, and the pole, the place corresponds to V prime. And the proof is just so now we can use the fact that we worked hard in the rational function field. So in this case, we have K, and we have F0, which is, so suppose X is transcendental, then F, which is Kx, let F0 be this field, then this is the rational function field, and F of, so we have this inclusion, and all we need to do is to, once we have this theorem, is to, okay, so we should, all we need to do is to find, so let's start with the valuation which is positive. So we just have to find the phi 0 from F0, which is just the rational function field Kx, to some algebraically closed field. So let's say the algebraic closure of the F0. So it's, yeah, it's maybe confusing because it's also the residue field, but this is, I mean, the algebraic closure of F star. And all we need to find is a place that send x to 0, right? So an element x, the valuation of x is positive if the place sends it to 0. So we need to find a place which maps x to 0, and then the theorem, by the theorem we can find an extension from f, which send x to 0. Okay, and what is this place? So, right, so every rational function with fg coprime, we saw that there is one place, just substitute 0, right? F0 over G0 if x does not divide Gx in Kx. So if the denominator is non-zero, then we can substitute, and otherwise just infinity. So this is a, yeah, so this particular place, you can check that x is mapped to 0. So the valuation that corresponding to the extension of this place will give this. And for this, we just, what can we do for this? Just, exactly, just take x inverse and the same, right, so like we saw today, then replace x with x inverse, and the fact that vx inverse is positive means that v of x is negative.
That's the way to explain what we know about the rational function.
Good.
Or,
Exactly. So the typical scenario in the following lecture, or maybe in the future, so we will have f, some finite extension of the rational function field, and these things we know really good. We know all the places. We'll see that in the next problem set, and we understand the divisor, the degrees, the dimensions. Everything is clear. And this, so to analyze what happens in f over k, we will use this and the extensions. So we will study the extensions, and later we will extend k to some L and extend it to, okay, later. So this in future, this is where Galois theory will play some part. So to understand the behavior of this, we will need to analyze the behavior in this extension. Yeah, but the base case is the rational. So good. Yeah. So suppose we have some place from a field F0 to an algebraically closed field L plus infinity, and now we have a field F which extends F0. So like, yeah, okay. So can we find a place from F to L that extends this? So when we restrict it to F0, it's the same as phi0.
Yeah.
And the theorem says that we can. Yeah.
Maybe just again, addition can get a ribbon piece or maybe what happens if or something.
So if L is not algebraically closed, then it will be maybe a bit annoying because maybe we'll need to take some algebraic extension of L above. So to avoid this thing, we take L. We can always increase the range, take L which is algebraically closed, and then it's sufficient to use L. We don't need to.
The residue fields are always finite.
Right, the residue field is not L, it's some subfield of L. Okay, yeah. Yeah, so I can write the residue field, and I can take any set that field that extends that contains the residue field. Yeah. It is that depends on K. Usually, if K is finite, then no, it is not.
Yeah, so the question is like, does it change anything when you go to like F instead of F0? And the answer is yes, because the residue can also make it bigger.
Oh, good. So we will discuss it. We will see. Yeah, but it potentially it can be larger. This is just this is exactly the ramification index, right? The dimension of the residue field above over the residue field below. So we will see it in, yeah. So is it clear? Statements? Okay, so let's talk about divisors. So only divisors, finite formal sums, not pseudo divisors. So let f over k be a function field. Then a divisor is just A is a divisor if A is just a formal sum where P is a place of F and NP is some integer with NP 0 for almost all P. So this is the definition, and this is a group with respect to addition, adding addition pointwise. And actually today we saw the subgroup P of the principal divisors. So it's just a way to take a non-zero function in F and obtain a corresponding divisor in which how it is defined. It is just for every place what is the coefficient, the valuation, right? And actually today we saw that this is a divisor. So a priori, we don't know that this is 0 for almost always, but today we know that we can split it to the 0 divisor minus the pole divisor, and both are divisors, and they have the same degree, which is this, the dimension. So what is the degree of x? The degree of this minus the degree of this. And since they both equal to this is degree 0. So all the principal divisors are of f degree 0. And we also saw the divisor class group, which is just the D mod P. So it was just 2 hours ago, so okay. So in fact, we showed in class that every principal divisor has degree 0, but the converse is not true in general. So there are divisors with degree 0 which are not principal. But so the exercise show that every divisor A with degree 0 in any divisor of the rational function field kx over k of degree 0 is principal. Okay, so if we consider the rational function field and take a divisor of degree 0, then it must be principal. So we'll see an example, and the example will convince you. So what are the divisor of the rational function field? So there is one special, the place at infinity, and the other are just irreducible polynomials over k, monic irreducible polynomials. So for example, if A is, let's take a example. So 5p1. So p1 is just what is p1? It's the place corresponding to the polynomial x minus 1. Substitute 1 minus 3 p2, maybe plus p of x squared plus 1. Maybe the example is in, say, rx over r. So we have a place of the polynomial x minus 1, x minus 2, maybe x squared plus 1. And what is the degree?
Yeah, minus.
So the degree here is 5 times 1 minus 3 times 1 plus 2. The degree of this place is just the degree of this polynomial. So it is 4. So let's say minus 4 p infinity. So this is a place of degree 0. And what is the function f such that f is a? So it should have at 1 a 0 of order 5. At this, okay, so what is f? Mm-hmm.
X plus 1 over x minus 2 squared.
Good. So exactly. So this really gives us suggest to use this f, and now we just need to verify that indeed if we take that this equality holds. So for example, y vp1 of this divisor is vp1 of a. So with vp1 of a is 5, and vp1 of this divisor, by definition, it's vp1 of the function f. And what is vp1 of the function f? The valuation that corresponds to v1, we should ask ourselves, take all the powers of x minus 1 from here, the powers of x minus 1 from here, and what is the power that you get? It's 5. And similarly for this, and all the others give 0, and we only need to check that also the infinity place. So in the infinity, we have in A, Vp of infinity is just the coefficient minus 4, and in A, and if we take P infinity of the divisor of f, it's just V infinity of the function f. And what is this? So if you remember, what is the valuation? Right, it's the minus the degree of the numerator minus the degree of the denominator. So the degree, it's minus the degree of the denominator is 5 and plus 2 is 7 minus 3. So it's minus 4. So it's good. So this was a specific example in Rx, but in general, if I give you A, which is, say, some subset np times p plus m times p infinity, then what should be f? A rational function whose divisor is just this thing. So just imitate what we did here. So every place here, which is not infinity, we can associate a monic irreducible polynomial, right? For P1, it was x minus 1. For this, it was this. So let's call this polynomial P with slightly abusive notation. So we just take the product of all the P's, each P with this power. And you can check that this indeed, this is a rational function. And you can verify, and it's in the notes, that f, the divisor of f is exactly a. And they're just quite similar to this. Okay. So in the rational function field, a divisor is a divisor has degree 0 if and only if it is principal. So if it has degree 0, then it is principal. We just showed it, and we know that always a principal has degree 0. So what is the group C for the rational function field? So let's see. So we have the degree, which maps, it's a ring homomorphism, group homomorphism. Yeah. Just to make sure that this is irreducible. Good. Finite field. I guess some finite fields are good. Yeah, maybe C is not good. So. Reducible, exactly.
So why did
yeah, the places correspond to are coming from the reducibles, monic reducibles. Okay. So So now the next question is, what can we say about this divisors class group for the rational function field? So let's see. So we have the degree takes a divisor to its degree, and we know that it is a group homomorphism from D to which group? Z, right? Exactly. So what is the kernel? All the places that their degree is 0. This is exactly P. So good. So the kernel is exactly P, specifically for the rational function field. So we know by the first isomorphism theorem that D modulo the kernel is isomorphic to the image. But what is the image of the degree? So it's a subgroup of Z. And is 1 in the image? Yeah, so for example, the place P1 is a place of degree 1. The corresponding irreducible polynomial is x minus 1, degree 1. So in fact, the image is Z. So C is just isomorphic to Z. Okay, questions?
So this is too only for K of X, right?
For K of X, maybe
Maybe it can work
maybe for other, but yeah.
But we know it only for K of X.
Yeah.
The kernel of the degree is only on K of X.
Right. In general, the kernel can be larger. Like there may be non-principal divisors with degree 0.
Yeah.
But not in the rational because of this. Yeah. Okay. And in fact, next week when we define the genus, then you can show some generalization of these things. So it's not only for the rational, but okay, maybe I'll say it next time. So, okay. Okay, so okay, so let's finish with something nice, which we'll continue next time. So the trace and the norm. So I guess you're already familiar with this thing. So let's define. So suppose we have a field extension L over K, and some element A in L. Then we can consider the following map from L to L. We just maps every element X to alpha times X. So mu alpha just multiply by alpha. So this is what can we say about this map? Good, it's K-linear. It's even L-linear, but K-linear map, right? Since the mu A of X plus Y is alpha X plus Y, it's alpha X plus alpha Y. So it's mu X alpha plus mu alpha Y. And also with the scalars. So it's K-linear map. So what can we do? So let M alpha be an n matrix, be the matrix representation of mu alpha. So what is the matrix representation? So we need to fix some basis with respect to a basis V1 to Vn of L over K. Oh, maybe I'll add the finite. Okay. So if it's an extension of degree n, we can find the basis V1 to Vn, basis of L over K, and then the MA would be the NLN matrix representing this map, from like in linear algebra. Okay, so the trace of the extension is a map from L to K given by every alpha in L is mapped to the trace of this matrix. So the trace is just the sum of the elements of on the diagonal. And what is the norm from L to K? Every alpha is mapped to the determinant of M alpha. Good, so this is my next question. So is it depend on the choice of the basis? So MA can change if we change the basis, but the two such representations are conjugates, right? So, and the trace and the determinant of a conjugate matrices does not change, right? So if B is pi minus 1 AP, then the trace of this is the trace of trace A and trace B are the same, and that A and that B are the same. So it is well defined. It does not depend on choose arbitrary basis. Maybe the matrix will change, it will, but the trace and the that will not. Okay, so it's just from linear algebra, right? So to change a basis, you need to multiply with the matrix P with. So this is the definitions. So these are two important maps from L to K. And next time we will see some properties of this and a nice application in a specific function field. Okay.